All right. Thank you everyone for being here. I want to talk to you a little bit today about our research in container level energy observability for Kubernetes. If I select the right screen. Okay. Yeah. That's it. Forgot to turn it on.
Yeah.
Okay. In existing research, we look a lot at energy efficiency, waste of energy in data centers. We look at over provisioning in cloud solutions. We look at all kinds of stuff to optimize energy usage as much as possible for data centers, for Kubernetes clusters, for virtual machines, basically any system you can think of. Most of these existing solutions, they optimize entire clusters or data centers at once, because you can target a huge amount of applications with a single change. Think of a scheduler that optimizes for energy efficiency. Think of observability tools that allow you to turn off a VM once in a while. All solutions that save power. However, in the existing literature, there has been very little regard for the individual workload. So single applications and how to optimize those for energy efficiency. Specifically, what is missing is observability into the workload power usage in Kubernetes. And it might sound a little bit arbitrary to focus on this specifically, but the context here is that we wanted to look at energy efficiency in Kubernetes for our research, except there wasn't even a way to measure the amount of power used. So our research focuses on accurately measuring or estimating the power usage of Kubernetes containers based on external measurements. Well, why do we want to do this? Specifically workload observability, is to give developers or operations engineers that work with applications or Kubernetes clusters daily a way to measure power usage of applications. For example, they could choose to optimize solutions for energy usage, compare different approaches to solve the same problem, or something more simple. A developer just does their work, but you can instrument some alerting after a deployment. If the power usage of the application suddenly goes up, that might be a trigger to investigate more. And of course, measuring something like CPU cycles for this is simple, but it really doesn't tell you much. And a measure of energy, like kilowatt hours, is much more approachable to the average developer that might not work with these measurements or operations in their day-to-day. Basically, it's a way to start from the bottom up with optimizing. We want the applications themselves to be as efficient as possible. And from there, we can work on optimizing the clusters, the data centers, and everything in between. So this is the first step towards granular energy efficiency. Our approach is twofold. There is a state-of-the-art tool for measuring or estimating, I should say, the energy usage of a Kubernetes container that is called Kepler. It's by the Cloud Native Computing Foundation, where it has reached sandbox maturity. Spoilers are, this is not great, and I'll show you a bit of this later on. Secondly, we have built and evaluated a much simpler alternative tool based on a simple power mapping model that I'll go into a little bit later as a proof of concept, mainly to show that Kepler's shortcomings aren't a fluke of the underlying Kubernetes architecture. Important to know is that we consider two types of power for both of the tools I'll be talking about, because system power isn't a single number. By simply turning on a server, you use power, and that power isn't really associated with any specific workload. So we divide this into idle or static power and dynamic power. And dynamic power is the most interesting to us because that is something that is specific per container and that is influenced by the workloads that are running. So to go a little bit into Kepler first, Kepler's main goal is to estimate power usage or energy usage per Kubernetes pod in a whole Kubernetes cluster. And it does this first by taking measurements of both platform and component power. Platform power here is all the servers that the Kubernetes cluster runs on in total, all the power it's using. And then component power tries to divide this up between, for example, the CPU, the RAM, any GPUs that may be present, all the different components of the system. And to do this, it uses, among others, Intel RAPL, which is a kernel level tool that allows Intel CPUs to report power usage for different components. It uses the Redfish API, which many servers implement at a hardware level. So you can actually ask the power supplies for the current wattage, for example. And it can also use software estimations. And it can use some of these at the same time. Some others are more exclusive. It's very configurable in how you approach this. And it's also based on what metrics you have. If you have a cloud solution, something like a server management interface is obviously not going to be available. And Kepler exports its findings after processing all to Prometheus and Grafana for observability reasons. So the first step on our research was an experimental validation of Kepler, see if and how it actually works. And the goal here is to run Kepler with workloads and validate its estimations against real measurements that we take of servers. And we look both at node metrics, so the platform power and the total usage for a server, and we look at container level power metrics. Now I have a diagram here, and I'll zoom in a little bit because it might not be very large. That unfortunately, zooming doesn't work, but I'll go over it quickly, just talking about it. The main setup consists of a Kubernetes cluster, which is this part, where we run Kepler and also have cAdvisor, which is internal to Kubernetes, which tells us something about resource utilization. External from that, we have the Intel CPU and its kernel modules, which is RAPL that I talked about before. The power cap is the specific kernel driver that we're using to interface with it. There are multiple. Power cap is the simplest. And we have IDREC, which is provided by the Dell server that we have run our experiments on. We use some external software to get the readings from IDREC into Prometheus. And we also read both Kepler and cAdvisor into Prometheus, where we do our data processing later. Based on these results, we see significant differences in Kepler's output and real-world measurements, and I'll show some examples on the next slides. We had some containers that were not running. They were completed, but they did account for significant power usage. We had some power that was misattributed to non-existing processes where Kepler just got confused and said, well, I don't know what this is from, this power usage, even though it was a very simple example and it should have been very clear where the power was coming or where the power was being used. And we had some instances where the software estimation, which Kepler uses when no other sources are available, failed altogether, where it reported single-digit watts being used, even though we had a big kilowatt server that our experiments were running on. However, the node metrics, they were quite good. In our best cases, they align precisely to the source data, even if the source data might not be fully accurate. That's not Kepler's fault, but I'll talk about that a bit at the end. This is the first example I'd like to show you, and what we see here is a number of Kubernetes namespaces and their power usage according to Kepler over a couple of minutes where we ran our test. And in this test, we had a single pod in the stress namespace, which is the purple line you see here, that ran the CPUs to about 50%, then turned off for a bit, ran the CPUs at 50% again, then turned off. And what we see is sort of what we would expect. Obviously, the namespace with the largest stressor exactly follows the curve of our test, which is good. But what we also see is a bunch of namespaces with significant power usage that we wouldn't expect. And the one I'd like to get into specifically is the idle namespace. This had approximately 16 containers running, or not running. They were completed, but Kepler tells us that they are using 100 watts of power. In our eyes, this is a significant shortcoming of Kepler, because obviously containers that are off shouldn't be using 100 watts, and in reality, they aren't. Another test, we tried to get Kepler to do some more interesting behavior. Because we found that these ghost containers are using power, we wanted to investigate what happens if we delete them. And this is what happens. We again see the purple line is the stress namespace, the orange line is the namespace without any running containers. And we have 3 vertical markers. On the first one, we start a stress test. I recall it was approximately a quarter of the CPUs running, and we see indeed that the purple line goes up as we would expect. At the second line, we delete all the inactive containers that are using power even though they are not. Yeah, Kepler says they're using power even though they are not. And we see something very interesting happen, which is the system namespace. The brown line is reported at approximately 100, 120 watts. The system namespace doesn't exist. This is Kepler basically hallucinating and saying, I don't know, I'm throwing my hands up. I don't know where this power is coming from, even though we had only one significant workload. So in total, we've observed Kepler, giving power attribution to containers that are idle. We've seen Kepler totally get confused when the configuration of the cluster changes and we delete a bunch of containers. In total, not a very good tool that we can use for other research as we were intending to. So to showcase that this is not a fluke of the Kubernetes architecture itself, we developed a tool called KubeWatt, which is very proof of concept, but we simply wanted to do some calculations ourselves and show that Kepler's shortcomings are not inherent to Kubernetes or to this measurement altogether. This works on a very simple power mapping model, which is we determine the dynamic power fraction, and then we scale that power value to the CPU usage by container. Obviously, this is very limited. I'll talk about that a bit more later, but it should give us a picture of what is happening under the hood. The data collection here was using Redfish API, which is the server management interface. So that gives us a very precise reading of the power supply itself in our test. And we use the Kubernetes metrics collector for the CPU usage data, which is internal to Kubernetes. It always tells you the number of CPUs that are being used by any container. And again, we export this to Prometheus. To calculate the fraction between static and dynamic power, we have built 2 methods doing this. One is to measure the cluster at idle for some time, and that simply gives you the idle value. Of course, it's a bit more complicated than that because the control plane on the cluster is running. In our case, we simply accepted that that is included in our idle value, and that's the power that we attribute to containers later on includes some of the power used by the control plane. Future work is looking into how to get this better and actually get the control plane as a separate value. Fortunately, we were out of time to do this. The second way, because you don't always have a cluster that is idle, is to measure the cluster while running for some time. And with some time, I mean 24, 48 hours, and then find the static power value with a simple regression. This fraction is non-online measurement in this case. You measure it once, and then you instrument KubeWatt with this. This is fine for the short test we did because you can expect the cluster and the environment not to change much. But there is being novel work done by a student in Sweden right now on getting this online in KubeWatt, trying to continuously update this value based on other external factors. Then the estimation mode, which is the most important part of KubeWatt. As I said before, this divides the dynamic power per node proportionally to the container CPU value per node. And due to its remarkably simple design, in this case, we found that it was able to overcome some of the limitations that we found in Kepler. So power was attributed to containers using the CPU, and it was able to do that correctly. And we also saw that no power was attributed to containers that are not running, simply and only because Kubernetes does not report these in its metric API, which is what we should expect. Then a very simple example. This is the same test as I showed before, where we saw the system namespace, it's not the right word, but the system hallucinations of Kepler. And we see it's remarkably simple. Of course, some of the namespaces here are filtered out because we included those in the idle power value. And for the ease of the test, we decided not to put those in the figure as well. And we see two things. The static power value is, of course, not changing because we tested this only once. And we see our stress namespace rise to about 50 watts, stay static over the test because the amount of CPU utilization we use over the test does not change. And then at the end of the test, we see it neatly go down to 0. Of course, there are some limitations to our estimation mode. It is based on real-world measurements in this case, and those are very often not available. Think, for example, of a cloud environment where you get a Kubernetes cluster on demand. In that case, you have no real access to the underlying servers. You might not even be guaranteed a server to use all on your own. Unfortunately, during the research and also in previous work, we found that no sufficient software solution exists yet. It's really at this point not possible to get metrics from the CPU and the operating system and estimate how much power are we actually using with any sort of accuracy. Also, KubeWatt only supports the CPU-based estimation. We did this because we were running a proof of concept where that was more than fine, because it's the largest power draw in, well, non-GPU or FPGA or any other accelerator scenario. If we were to develop KubeWatt further, obviously, we should implement support for the multiple components like CPU, GPU, or any other parts of the system that are using significant power. But to conclude, we have looked into the state of the art for container level energy observability, and we found that the generally accepted tool has some significant shortcomings. And subsequently, we have demonstrated using a simple proof of concept that it is possible to get some, well, arguably crude measurements that reflect the real world scenario more accurately. And using this in the future, we hope to develop it further, especially collaborations with other students and other universities as they are happening now, to either improve Kepler to get it more accurately or to influence other tools and other research to more completely describe and research this problem. All right, thank you. Now's the time for any questions. I've tried to, mostly. I have made one or two GitHub issues outlining some of the problems. Even before starting my research, just exploring Kepler, there was a wild amount of weird measurements in newer versions that were completely unrealistic. At that point, I was testing on a 35-watt machine at home, and Kepler sometimes reported tens of hundreds of kilowatt being used, which, I mean, my house would have lit on fire at that point. I made an issue and they responded once or twice, but after that, they basically ghosted me. So after this research, we debated making another issue. I talked to the Kepler team on another chat, at least one member of them, and they said that they were very busy with other things. I think some of these issues they're aware of, some of them they're not, which is why we went forth, made our own KubeWatt implementation to at least show that it is possible at some level to get more accurate with fewer issues.
I have a mini question because I told you talking of software and I completely understand what kind of foreign places. So just to take the point, maybe there is someone that is going to just for you. Yes. So maybe we can continue the discussion.
Yes.
But I think we will be presenting in the parallel and the same time on Thursday. You're presenting.
I'm on Thursday as well. Yeah. But let's talk after this. I'll stop the recording. Thanks everyone online for attending.